on the periodic table for these atoms is the sum of all of the isotopes. So that's what this equation here is telling us. So in doing this problem, as you can see, I put to the side here that we need to make sure that we're using the fraction of that number, right? So this is 11.17%. And when we're okay, so first question, how did you get the 0.787 and 0.1117? Really, it's just moving this decimal point over two spaces. So that's how you just convert it from its fractional to its, or from its percent to its fractional. It's just moving the decimal point. Okay, so it looks like everyone is finishing up. So let's go ahead and talk about this one. Real quickly, someone asked if I could send the final review packet. So again, the packet you're working on is for this session, but here's the final review packet if you need it. Okay, so let's go ahead and talk about this redox reaction problem. So remember, for doing redox reaction, we need to find the oxidation number for each element in the problem, okay? So for this problem, I don't really like to do this, but I am just gonna go show you all the numbers, and then we'll talk about the specific ones and where I got them, just because I'm working on PDF. But for aluminum, you should have an oxidation number of 0. If you need the specific rules for those, they are in the final review packet. So oxidation number of 0. For H2SO4, this is a more complicated one, so I usually like writing it out, and I did it down here. So let's talk about how I did H2SO4. I'm sorry if it's a little messy, but I'm going to try and walk you through it. So real quickly, what we need to know, what I like to do about H2SO4 and other problems that also include a polyatomic ion as part of it, is I like to separate the polyatomic ion from its partner. So here in this case, we have SO4, 2- is the polyatomic, and it is paired with a hydrogen, or 2 hydrogens specifically. So something we need to know about the rules is when we're doing this, the compound as a whole needs to have a charge of 0. However, that's not what we're focusing on. What we're focusing on is the charge of individual elements in the actual compound. So what I like to usually start off doing is looking at either side individually. So I need to make sure that the charges on my left side cancel out with all the charges on my right side. Well, I know that the charge of my polyatomic ion for SO4 is 2-. So that means the charge on the right side of my line is 2-. In order for my overall compound to have a charge of 0, my left side needs to have a positive 2 charge. This makes sense because I have 2 hydrogens, each of them containing a positive 1 charge. So +1 charge here times 2 is a +2. So we know my hydrogen if I didn't use the rules, which the rules say that hydrogen has a positive 1 charge in compounds. But if I didn't use the rules, that's a good way to just clarify that hydrogen does have a +1. The next thing we need to figure out is my SO4. I need to know my S and my O. So because my S is not in my rules, my sulfur, it doesn't have a given charge in my rules. I put an X there because it's an unknown to me. However, in compounds other than hydrogen peroxide, oxygen has a -2 charge. So I do know that. And what I like to do, because my brain works in a more math way, so I like to plug it into an equation. I know that the sum of my charges, or the sum of my oxidation numbers in SO4 have to equal -2, because we're just talking about my polyatomic. So I know that I have an unknown charge of X, and I only have 1 sulfur, so it's just X. If I had 2 sulfurs, I'd have to put a 2 here, because I mean I have 2 charges. But in this case, I only have 1 sulfur, and then my oxygen has a -2 charge, right? That's why I put it in parentheses here. However, I have 4 oxygens, so I need to make sure I multiply that charge by 4. And all of this needs to be equal to -2, because again, I'm only working on the right side of my problem. I've already solved my left. I'm only working on this right side, and the right side has a charge of -2. So when you solve for X, you get a charge of +6, okay? And this method can be used, it can be applied to Al2SO4, 3. Over here on this side, it can be applied to any of those bigger compounds, the more confusing compounds, as long as you just break it up in half like this. So like you guys should see here, I also wrote out my Al2SO4 in case you wanted to see the work for that. It's the same exact process. Okay, so I got a question. So how do we get the oxidation number for aluminum on the product side again, and why isn't it +2? Okay, so that's a good question. So as you can see here, I kind of worked out this problem over here. So we have 2 aluminums, and if you think about it, so here's how we have to work it out. So SO4 has a charge, like I said a little earlier. I'm going to write it in a text box. SO4 has a charge of -2, okay? Right? However, we have 3 SO4 compounds. So when we're solving for the overall charge on both sides, I need to break it down, right? So if I have -2, if I have 3 -2 charges, right? Because I have 3 of these SO4 compounds, I have to do -2 times 3, and that'll give me an overall -6 charge on my right side. We know that both sides have to equal out, which means I have to have an opposite charge, which is +6 on this side. Well, I know I have 2 aluminums, right? So I have to divide that +2 charge, or +6 charge, sorry, by 2, because I've got 2 aluminums, which would give me a +3 charge on both of those aluminums. Okay, so that's where I'm getting that +3 charge on aluminum on the product side, this one right here. Does that make sense? Okay, perfect. So it does get really tedious, but that's why practice is key on these problems. So if you are struggling with redox problems, I would just go to the back of the textbook and do a whole bunch of practice problems until it clicks, because that is really just the best way to nail down these problems. So for this one, remember our little, yes, you will have to memorize the charge rules. They should be on like the first or second page of that packet that I've given you, the review packet. But yeah. So remember this little rule here, oil rig, oxidation is losing electrons and reduction is gaining electrons. That will help you determine which one is our oxidizing and our reduced, right? So just to review this, aluminum goes from a 0 charge to a +3. Remember that the electrons have a negative charge. So when we remove them, it leaves our product, or it leaves our atom with a positive charge. So 0 to +3 is actually losing electrons, meaning that is the oxidized one. And I know it might be hard to see, but there's a little OX here that symbolizes oxidation. And then in the second part, there's hydrogen going from a +1 to a 0. When it's getting more negative, it's going, I imagine it on a number line, going from a positive side to a negative side. When it's going towards that more negative side, it's gaining electrons. We are giving it negative charges by adding electrons, and that is reduction. So reduction is gaining of electrons, and that's why I did it here. Now the question specifically was asking for if it was a redox or not. Remember the rules for if something is redox, it has to have both something oxidized and reduce, right? It has to have both of them together. So this is a redox reaction. However, if say they gave you a problem where only one thing was oxidized but nothing else was reduced, that would not be a redox reaction because both need to be occurring, okay? So do I have any other questions on number 4?
Could you scroll down just a little bit?
Yeah, like scroll back this way. Okay, so what are the agents? Yeah, so, oh, I forgot to put that, I'm sorry. So let's talk about that real fast. So remember that the thing that is being oxidized is the reducing agent. Thank you for reminding me to do that. So the thing that is being oxidized is the reducing agent. So which element here is being oxidized? Aluminum. And aluminum again, with the reducing agent and the oxidizing agent, we only look at the reactant side. You never touch the product side. So if I know your exam isn't multiple choice, but if they ever gave you options to select a product as an oxidizing or reducing agent, that is always incorrect. Your oxidizing and reducing agents will always be on the reactant side, no exceptions, okay? So aluminum is going to be your reducing agent, okay? Because it is the one being oxidized. However, let's look at my oxidizing agent. This is where it gets a little bit trickier, but which element is being reduced? Should be hydrogen. Does that mean hydrogen is the oxidizing agent, or is there something more that we should put for the oxidizing agent? It's kind of a complex answer.
Is it hydrogen sulfate or sulfuric acid?
Yeah, exactly. It needs to be the whole reactant, the whole compound, right? So it's H2SO4 is the oxidizing agent. Then we didn't have a bigger compound for aluminum was because aluminum is actually alone, okay? So in another problem, maybe they give you a reducing agent. Maybe they give you a reducing agent with a bigger compound. Maybe aluminum is part of maybe it's aluminum oxide. So it's aluminum and an oxygen. So if that was the case, then aluminum would have to be, the answer would be LaO. So you have to include the entire entire compound as part of your reducing agent and oxidizing agent answer. So the reactants are the agents, yes. So your reactants, one of the two will be oxidizing and one of them will be reducing if both oxidizing and reduction occur. But yeah, they will be your agents. Sorry if I left that off my key, I completely spaced that. Okay, do I have any other questions? There's a whole bunch of answers. So aluminum is the one being oxidized. H2SO4, or hydrogen specifically, is the one being reduced. The reducing agent is aluminum, and the oxidizing agent is H2SO4. And it says, is it a redox reaction? And the answer is yes. So there's a whole bunch this is a very dense question. There's a lot of answers to this one. So there's a whole bunch. Any other questions? Okay, so let's go ahead and move on to this one down here. An organic chemist isolates colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask in boiling water, which vaporizes the liquid and fills the flask with gas. She then closes the flask and reweighs it, and she obtains this volume here, and she has this temperature as well as this pressure. And then she also has the mass of the flask and the gas together, and then the mass of the flask alone. So these values over here that I wrote over here, those were just knowns. They helped me pull it out of the problem and put it into an easier way for me to read. So it's whatever y'all need, but those are just part of the problem. And it's asking us to calculate the molar mass of the liquid. So go ahead and take a minute, solve for the molar mass of the liquid, and then we will discuss when y'all are done. And as always, anything that I don't cover in this session that's on this packet will be on my next packet, which is tomorrow. Okay, so I got a question. Is this a PV equals nRT problem? And the answer to that is yes, in a sense. It's going to be using the basic foundation of PV equals nRT, but if you will recall, we used a whole bunch of adaptions to the PV equals nRT, some that included density, some that included different types of partial pressure. So you're going to be using one of those to solve this problem. So it's kind of an adaptation to the PV equals nRT problems that we did. Okay, does anyone want more time? I don't think that you will be given those formulas. In the past, they haven't. I don't think they're changing it. So those would be something that you would have to memorize. There are some exceptions that they do put on those equation sheets, but it kind of depends on the semester and what the professors agree on. So that's something that you'd have to like specifically ask your professor what equations they will be providing, because they don't. I can tell you they don't provide all of them, only some. Okay, so let's go ahead and talk about this. So the first thing that you guys can see I went ahead and just made sure I circled all of this information, and so I didn't lose any of it. I listed it over here. And then I also did I took the difference between the mass of the flask and gas and then the mass of the flask, so I could just get the mass of the gas. So I know it's a tongue twister, but this over here is the mass of the gas, which is what we care about, okay? We don't really care about the mass of the flask. So first things first, this is the equation that I was using. So again, it is an adaptation. It's an adaptation for the molar mass. So we use density and molar mass to kind of moves things around in this equation to make it work. So this is one of the equations we talked about. This is adaptation for molar mass. And you should have everything you need to plug in. You shouldn't need to do any outside work really to just get this answer. So I went ahead and just plugged those in. The mass that I got, remember, was 0.582, which is the mass of the gas, which is I took the difference over here. I put it over my total volume of the gas, correct? So that should be, or the volume of the flask, which was 213 milliliters. I went ahead and converted it to liters. Okay, my molar mass, it should be an appropriate way of doing the problem. But it really, you can just manipulate as long as you're keeping track of those units, making sure you're not leaving anything else out. These equations were manipulated, so you can do it yourself. I personally just thought it was easier to memorize the equations, but as long as you're keeping track of everything, it should work out fine. Yeah. Oh yeah, exactly. She said if you accurately use the algebra to manipulate, it will work. 100% right. Okay. And that's so they haven't decided yet. So hopefully, yeah, pray for multiple choice. Hopefully it's multiple choice. I'm praying for y'all. Okay, so let's go ahead and talk about the second one. Oh, yay. Okay, so in a study of O2 uptake, my next packet, by the way, has a lot of multiple choice, so we'll get some practice with that as well. So in a study of O2 uptake by muscle tissue at high altitude, a physiologist prepares an atmosphere consisting of 79% mole of N2 and then 17% mole of this isotope of oxygen, 16O2, and then 4% mole percent of another isotope of oxygen, which is 18O2. They tell you that the 18O will be measured to determine the O2 uptake. So we're going to be focusing on, that's why I circled this one here. And then the total partial pressure is 0.75 atmospheres. I wrote over this one. I don't know if I fixed it in y'all's packet, but I think I accidentally put STM. It should be ATM. To stimulate high altitude, calculate the mole fraction and partial pressure of 18O2 in mixture. So when y'all are done with this one, go ahead and let me know, and then we will talk about it. I'm going to give y'all just a couple more seconds, and then we will go ahead and get started. Okay, so let's go ahead and talk about this one. It is just another type of, in a sense, P equals nRT because it is a pressure problem. Okay, so, okay. It's in that same category. It fell into that same chapter. It's not using P equals nRT, but it's in that same, again, the same area of, it was on the same exam, I guess what I'm trying to say. So let's go ahead and talk about this. So the first thing, it's really asking for the calculate of the mole fraction and partial pressure. So in order to do both, if you're familiar with, if you have reviewed the equations, and it was a while ago, so I understand not being 100% sure about the equations, but we should know that there is a partial pressure equation that incorporates mole fraction. So if you're doing these types of problems, it's probably smartest, if you're looking for efficiency and time and all of that, to calculate the mole fraction first, followed by the partial pressure, because we can use the answer for this first part for the second part. You can do it both ways. But this is just kind of like a time saver. So we're finding the partial pressure of 1802. And as you should remember, to find the mole fraction, you take the mole percent over 100. Okay, so pretty simple math for that. But then we need to find the partial pressure of the same gas, the same gas in the mixture, which is 1802. So in order to do that, you should know that the partial pressure of 1802 is equal to my mole fraction times the total partial pressure. So I know I didn't write the equation down, but really all it is it's the mole fraction, which is 0.04, times the total partial pressure. So I can go ahead and write that so we don't have any confusion. But that 0.75 is the total partial pressure. So if you think about it just mathematically, if you do multiply that percentage by the total, then it will give you about that percent of the percent of the total that corresponds to our gas in question, which is 1802. So that got about 0.03 ATM for that partial pressure. Okay. So just more on pressures. Do we have any questions over that one? So the formulas, let me just pull it up real fast. I'm gonna pause my sharing real fast and pull it up on my equation sheet so that y'all can see them. Give me just 2 seconds. So I'm having trouble finding it. Okay, really just the equation. They're in your review packet if you need that, but the equation for mole fraction is the percent. It's basically it's the number associated with our gas in question. So it's going to just be a percentage, right? You're going to take the total on the bottom. So in this case, the total is going to be 100%. So you do the total on the bottom, and then you do that. It could be moles, it could be mole percent, but whatever the units are, you're going to put that number of the specific one on top. So because we're talking about 1802, you're really just going to find the fraction. So because we're talking about mole percent, you're going to do the mole percent of the gas in question on top divided by the total, and that'll give you mole fraction. The equation for this partial pressure is really just mole fraction times this one's mole fraction times total partial pressure, and that will get you the partial pressure of a single gas. So this one really is just a fraction, right? You take the thing in question and you divide it by the total. So 100 on the bottom will be your total, and the gas in question goes on top. okay? There's different ways to write this equation, but those will be found in your review packet with the equations, okay? So I feel like they would ask the reverse, like give the partial pressure and give the mole partial pressure to find the mole percent. It's possible, but really, as long as you do have those equations, you can solve for it either way. So just know that your mole fraction is the thing in question over the total, and then partial pressure is of a single gas, of a gas in a mixture specifically, is going to be that mole fraction up here, and then times the total pressure. But they can ask it in any number of ways, as long as you have those equations to work through it. Okay, and those equations all should be on the review packet that I gave y'all today. Okay, so let's go ahead and move on. Which of the following compounds would be insoluble in water? This one, y'all just go ahead and type your answer into the chat, and then I'll show y'all the answer for this one. Okay, perfect. So I'm seeing lots of D's, and that is the correct answer. So remember, this is just one of those solubility rules. You just have to memorize them. They should be included on that review sheet if you need them. But it really is just knowing and understanding your solubility rules. So yeah, PBS is the one that would be insoluble in water. Okay, so let's go ahead and do 8. Dental hygienist uses x-rays with this wavelength, and then to take a series of dental radiographs while the patient listens to the radio station, which is on this wavelength. What is the frequency in s to the -1, which is also the same as inverse seconds, or the same as hertz, of the electromagnetic radiation from each source? And then it says, assume the radiation travels at the speed of light, and then it's given. So go ahead and take a minute. Basically what we're doing is you're just doing conversions from, I always get this mixed up. I want to say it's amperes, but it might be Armstrongs. It's the symbol that matters. And then nanometers, both of those to hertz, okay? When y'all are done, let me know. Okay, thank you. It's hard because when you take physics, you start using amperes, and then I just get them mixed up. So thank you. So that symbol should be for angstroms, and then an A without the little dot on top is amperes. Yeah, physics is rough. Physics is a rough one. It can be fun, but it's a lot of work. I would say it's debatable. Physics 2 is the worst. Physics 1 and chemistry are on the same plane. I thought they were both really, really fun. Does anyone want more time? Okay. Take a couple more seconds and then we'll talk about it. No rush. Strong's, right? And this is a conversion. I have never seen them include it on the equation sheet. That could have changed since then. But it is good to know that 1 angstrom is equal to 10 to the negative 10th meters. Okay. So I got it to that point and I got us in terms of meters. Oh, it's on the periodic table? Okay, good. I'm glad. So on the equation sheet, looks like they have it next to the periodic table. So hopefully y'all don't have to memorize that one. And then the second one I did, I also took it just to meters, just because I'm going to use my speed of light to get it to the next part. So I got 473 nanometers, used just your regular SI unit conversions, which is 10 to the negative 9th meters for every 1 nanometer. And that should have gotten you to 4.73 times 10 to the negative 7th meters. And then in part 2, I used this equation here, which is the speed of light is equal to the wavelength times the frequency. And it's asking what the frequency is. So that's why I rearranged it this way. So you should have your speed of light, which is 3 times 10 to the 8th, over your wavelength. In this case, this one was 5 times 10 to the negative 11th. And in this one, it was 4.73 times 10 to the negative 7th, which I got for the first one, 6 times 10 to the 18th. And the second one, 6.34 times 10 to the 14th, both in inverse seconds, which is equivalent to hertz, like I said. So they could have asked for the units in terms of hertz, and you would still go about it the same manner because it is equivalent as -1 to hertz. Okay. Do you have any questions on this one? Okay. Hopefully not. Perfect. Okay, so this one should be a nice breather. H3PO4 is what is y'all's answer for this one? So first off, do we think it's an acid or a base? Okay, yeah, so I'm seeing, yeah, perfect. So H3PO4 should be an acid. Remember, the definition for an acid is it's willing to give up H atoms, or protons as we call them. So because it has 3 of these H atoms, we assume that when it's placed into an aqueous solution that it will give up that H. So it will be considered an acid. However, and remember, when we're talking about bases, the bases like to give up OHs. So usually you'll see something paired with an OH, and that'll tell you it's a base. So NaOH would be a good example of a base, right? Now, the next thing is dissociation. Our strong acids will dissociate completely. Our weak acids dissociate partially. And those are just kind of pure memorization. So I always say memorize your strong acids, and everything else that's off that list will be considered weak. And those should be on the review packet. But the answer is C, it is a weak acid. So how I would have gotten to this answer would just been, it's not on the list of strong acids that we memorized. Therefore, it is a weak acid. Okay. So good job on that one. Let's talk about this next one. So two pollutants that form in an automobile exhaust are, or first, does anyone have any questions on that? Sorry. Okay, so two pollutants that form in an automobile exhaust are CO and NO, and environmental chemists must convert these pollutants to less harmful gases through the following equation. And then, given the following information, calculate the delta H. So this is kind of like a Hess's law problem. Yeah, it does make chemistry really, really challenging to memorize everything they give you. Okay, so yeah, go ahead and do this problem. When y'all are done, let me know. But yeah. Looks like some of y'all are done. I'll give y'all just a little minute more. Okay, so I'm going to go ahead and move on with this problem. So, remember when I'm doing Hess's law problems, usually what I like to do is just rewrite them down below so that I have some room to manipulate them, because that's what we have to do. So that's what I did here. I just rewrote them. Remember, with Hess's law problems, we need to have our equation A and B basically sum up to create our final equation here, which is this given equation here. So we need to manipulate them in a way that will allow us to add them up to each other, right? So our first thing we need to look at is this carbon monoxide, so CO. It's on the reactant side in our final equation, and it's in the reactant side here, so we do not need to reverse. And then everything else, after I kind of decide that, I like to look at the next one and decide if I do need to reverse it. And I look at my N2 here. Well, N2 here is in the reactant side, but N2 here is in the product side. So that tells me I do need to flip this reaction. So that's what I did here. I flipped it and put NO as the reactant and these two as products, which means I have to make sure I add that negative sign here, right? Okay, so I added my negative sign, and then one other thing that I need to make sure I need to do, I looked at my nitrogen again, and nitrogen here has a 1/2 next to it. However, nitrogen here does not. So I went ahead and I added that 1/2, and remember what you do and that actually works out in our favor, because we know that nitrogen monoxide here needs to have a 1 coefficient, not a 2, so that works out. And then we also need to notice that O2 is not present in this equation at all, right? And by adding this 1/2 O2 here, it actually lets us use it up here. So this 1/2 O2 is a reactant here and a product here, and because they're on opposite sides of the reaction, they actually cancel each other out. So everything should be accounted for, which means you also need to put this 1/2 here because we added a 1/2 here in this reactant. Not in this reactant, in this reaction, sorry. So you need to make sure you remember that we don't do anything to this equation here, but we need to add a negative and a 1/2 to this one. And then you sum it up, and you should have gotten negative 373.3 kilograms. Or kilojoules, sorry. I don't know why that has grams. It should be joules. Do I have any questions about that one? Okay. So if you do, we can ask them at the end, but let's go ahead and move on. This one I kind of have the answer already seen because of this here. But what is the most likely formal charge on the oxygen atom in NCO minus? So real quickly, although you probably know the answer because of what I've seen, just try and work it out and justify it to yourself real fast before you type in that answer. Okay, so let's go ahead and talk about this one real quickly. As you can see, I kind of put this formal charge equation here, which remember is different from oxidation number and is actually really helpful in determining which, and it's needed in order to determine the formal charge, but it's helpful in determining which resonance structure is also most appropriate. But for this question specifically, we're just talking about resonance. So notice that the answer was A, and this is kind of why. Sorry. So really, for this one, we set it up appropriately, which is this one here. Make sure you include this negative charge on the outside of the brackets, just because we do have an additional negative charge, on, I'm losing my words, the compound, I'm sorry. So that's why you have to put that there. Also make sure that you are adding an electron when you're forming this compound here. So remember, if we're talking about specifically the charge on oxygen, we're going to look at our oxygen here. So we are going to have 6 valence electrons. That's going to apply to any oxygen, right? And then this part in the parentheses here, we have the lone pair electrons. Okay, so lone pair electrons for our oxygen, we have a total of 4, and then 1/2 of the bonding electrons. So I know I kind of abbreviated my words here, but 1/2 of bonding electrons. We have 4 total bonding, but we have to take 1/2 of that, so that's going to be 2. And when you do that, you get a charge, or formal charge, of 0. Okay, so question. We said, I thought if N would form triple bonds, it would if it could. So that's kind of a tricky... I see what you're saying, but in this particular problem, it's because our oxygen's in a place where it actually likes to form 2 bonds, so it's actually more favorable for this whole entire compound if nitrogen only forms 2 bonds as well. Nitrogen commonly forms 3 bonds, but it doesn't have to in order to be satisfied because it will accept lone pairs as an option. But oxygen is more electronegative, so we tend to satisfy our more electronegative atoms first, and then our lesser electronegative atoms second. So because our oxygen is more electronegative, we'll satisfy it in the way it likes to be satisfied, and that's usually with 2 bonds. It can only have 1 bond. Yeah, but hypothetically, if you move some electrons around, you could give nitrogen 3 bonds and 1 bond to oxygen. So that's kind of what I was saying. Like you can manipulate this a little bit and give nitrogen 3 bonds and oxygen and carbon 1 bond, and then put some lone pairs on the outside, and everything will be satisfied as well. But yeah, 100%, carbon can't have more than 4 bonds, so you can't just place a third bond here without also manipulating oxygen. But yeah, so the best kind of explanation for this is really we satisfy our most electronegative atoms first, kind of do what they want first, and then we go the rest of the way from there. So in this case, our formal charge on oxygen should be 0. Okay. These are good questions, though. This is like my least comfortable area in general chemistry is resonance structures. I never really loved resonance structures, which was tricky because you need them when you get to organic chemistry as well. Okay, so rank the bonds in order of decreasing bond length and decreasing bond strength from highest to lowest. When y'all are done with this one, just let me know. Hopefully it's one of the quicker ones, and then we will talk about it. Okay, so let's go ahead and talk about this one. Just gonna go ahead and show you how I did it. I labeled them 1, 2, and 3, so that's what I did here. But for bond length, my number 2, which is the bond between S and Br, should have the longest length, okay? Remember, it's dependent on what? How do we determine length when we're dealing with these? Exactly, electronegativity, right? So here we're gonna, like I said, I circled these F, Br, and Cl to determine which ones were based on their electronegativity. So because Br is the least electronegative, it's going to have a slightly longer bond, and then it goes downwards in that order. So chlorine is less negative, or a little bit more electronegative than bromine, which is going to have a slightly shorter bond, and then fluorine having the shortest of them all. And because it is the most electronegative, and it wants those electrons in the bond close to itself, which will then shorten the bond, okay? And then bond strength, we should know, is inversely related to bond length, right? The shorter the bond, the stronger it is. So we just basically flipped the order. The bond between S and F should be the strongest. Do you have any questions on those? That's really just another good way of them testing your knowledge on electronegativity. Okay. Oh, and I just showed you the answer for that one. Hopefully this one isn't too bad either because it's kind of the beginning material. But what is the formula of cobalt-3 sulfate? Perfect. Okay, so yeah, it is D. Really, it's just a matter of knowing how to do this. It's sulfate, so it's not SO4, right? It's just going to be sulfur. Or sorry, not SO4. Sorry, it's not going to be just S. It's sulfate is going to be SO4. I'm completely just messed up my words there. So it does include a polyatomic ion, and just make sure that you know that the sulfate has a -2 charge, and you have to bring that down to the cobalt. It's really just about, I kind of highlighted those differences there, really just about knowing where those charges go. Okay. All right. How many pi bonds and how many sigma bonds are in a N triple bonded to an N, both of them having lone pairs? So this is kind of like, yeah. Okay, so this is like last chapter's material, really towards the end. Okay, so yeah, 100% correct here. I kind of just drew it out so we can see it. But really, we know that in every single bond, there will always be at least one sigma bond. There's never going to be more than one. It's just going to be one sigma bond. And then the rest of the bonds, if the bond has multiple bonds in it, the rest of those bonds will be given pi names. So because it's an S3, it's going to have one sigma and the rest of them will be pi. Now, if they give you a double bond, it's going to be one sigma and one pi, okay? All right. And let's just do this last one. It's a multiple choice, and then y'all will be free to go. Everything else I didn't cover will be in my next packet. But when do this one real fast. When you're done, type the answer in the chat, and then we'll talk about it real quickly. Do I have any questions on the pi and sigma bond one? Okay, and y'all should see, like I said in my last session, that I would include more hybridization problems. You can see that I have some down below. We just haven't got to them. So, but they will be on my next packet. So how do you find pi again? So just remember that pi, yes, so there's always one sigma in every compound. And when we're talking about sigma and pi, we're counting the number of bonds. So here, as you can see, there's 3 bonds. At least one of them is going to be a sigma bond. I just chose the bottom one. It doesn't really matter. But at least one of these bonds will be sigma. How we find pi is just however many leftover bonds there are. So there are 2 other bonds in this, so they're both going to be pi bonds. So yeah, the lone pairs have nothing to do with sigma and pi. It really is just counting the bonds, okay? Does that make sense? Okay, perfect. Yes, so single bonds are just sigma. So if you just have water, for example, right? Though you have a single bond between a hydrogen and an oxygen, that will just be a sigma bond. You'll never have a pi bond in the compound water because it's just composed of single bonds. I've seen them do on the exams, they give you really, really big compounds, but they're already drawn out for you in a structure, like they're already drawn out in this kind of structure, and they'll say how many pi bonds are in this structure. So basically, I would just go through and count. Really, what I do is I count my sigma bonds, right? I go ahead and label all my single bonds as sigma, and then I go to every multiple type bond. So any bonds with doubles and triples, I always put 1 sigma, and then right next to it, I put how many extra bonds there are, and then you sum up all of the pi ones. So those, I've seen that. I can probably find one to put on my next packet for y'all if y'all would like that. But I've seen that a lot where they give you a really big compound and just ask how many sigma or how many pi bonds are in this compound total. So, okay, but I will go ahead and put that. Let me write a note for myself real fast. Sorry, I'm over time. Let me just, I don't want to forget. Okay, So I can see y'all's answers. Y'all put D, and that is correct here. So just remember, identify net ionic equations. Yes, I will. So for this one, you get rid of the spectator ions, right? That's what a net ionic means. You really are just looking at the solid, the product of the solid. So we look at the ions that form that product, that solid product. Okay, so here is the final review packet. Sorry, hold on, it's not going in. Okay, there we go. So there's the final review packet. I'll be uploading it again in my session tomorrow. And then everything I didn't cover today will be on my next packet. So I'm going to go back up to 1 and 3 real fast as requested. So there's 1. Yeah, so just a real quick explanation of 1 again. Really, it's just we use this equation and we just have to make sure we do it in parts. Really just make sure that you just clarify, you understand these numbers here, right? Yes, okay, perfect. And you understand the setup of the equation? It's just you're getting a different answer? Okay, so just to make sure we're doing this algebraically, like correctly, how I did this is I multiplied everything that I could together because we have to do that first, right? So I multiplied these two. And then I basically just, either you can add them together and subtract them, or you could subtract them one at a time, but I take the sum of these, or not the sum, but the product of these two right here, and I subtract it from my 24.314 or 313. So when you do that, I mean, I can do it real fast. Hold on. I'm not exactly sure what that number should be, but let me do it real quickly. 23.985 times 0.787 plus 25. Okay. So when I did that, I got 24.313 minus, I got 2.53. Okay, so that's multiplying these, adding them together, and then subtracting them from that, I got 2.5. And then from there, you should be left with 2.53 on this side and 24.986x on this side. And then I just divided the answer. So that should be divided by. And when you do that, you should get 0.10143, so on. So I think it's really just making sure you're getting that algebra, down and paired. Does that make sense? I'm sorry I didn't provide the full algebra there for you. Okay, so then I also got asked to show 3 again. So here's 3 for you. Hopefully you can read it okay. My handwriting gets messy sometimes, I'm sorry. Yeah, of course. All right, are there any other questions? Yeah, I am the president of the Medical and Dental Global Brigades. Well, right now we're on the wait list to go to Greece to help Syrian refugees this summer, but that may or may not happen depending on what happens with COVID. But that's where we're set to go as of right now. But yeah. Yeah, you can. So basically what we do for attendance on the actual trip itself is we require active membership the semester prior to the trip. So that would be this coming spring semester. So yeah, you definitely can still join. but there are even like, we do volunteer opportunities all throughout the semester. So even if you can't actually, like, even if you can't afford, or if the timeline of when we're in the other country, if it doesn't match up, you still can, be part of the org and volunteer and that stuff. But I mean, if you really want to, you can email me and I can send you some more information on how to join. And we use a website called Band to kind of keep everyone up to date on all of that. So we can definitely add you in that. Yeah, we'd love to have you. It's a lot of fun. It's a lot of work, but I mean, being a member isn't a lot of work. Being president is a lot of work, but the general idea of it, we do a lot of cool stuff. So it's been a lot of fun. I've sadly I was supposed to have gone to like 3 brigades, but our Panama one this past summer got canceled because of COVID. So I've been to 2 countries for it, and it's a lot of fun. And it's a really great experience. So I'd highly recommend it to anyone, in the pre-med field, even not in the pre-med field. Like, it can really benefit anyone, because you don't really need to know any medical anything before you go. We teach it all to you. But yeah, it's a really good experience. It's a lot of fun. Yeah, of course. All right, if y'all don't have any other questions, y'all have a great night. Good luck studying, and hopefully I'll see y'all tomorrow in my other session. But if you do have questions, feel free to email me, and I can answer them that way.